Hello AP Calculus, here is the second video of lesson 2.4, section 2.4, part 2, lesson 2 of section 2.4. We're basically doing a reprise of these concepts just to make sure we have those solidly, implanted in our brains. So I talked about this a few days ago. The idea here is that if coming from the left of a number and coming from the right of a number limit-wise yields infinite values, then we're talking about vertical asymptotes at these spots, which means that ultimately whatever else is happening in the problem, it's basically like yielding to like this infinite value. So we're either going to have positive infinity or negative infinity for, I guess, problems, limits that yield this kind of structure. So the first thing we need to do is we need to decompose a function like this into x minus 5, because 5 is the domain issue that I'm assuming is going to occur on the bottom here. But maybe we shouldn't assume. Maybe try plugging in the bottom and see what happens. So 25 times 5 is 125. 5 cubed, 5 times 5 times 5, is also 125. So the bottom yields a domain issue. So we do need to make this split up happen. So, we can do several things. I mean, we can technically factor out a 3 up top if we wanted to. And the bottom, we could take out an x. That would give us 25 minus x squared. Then we've got 5 minus x, 5 plus x, difference of squares factoring. And really, this is the one that's got the domain issue. But it's not written in the format that points us in the right direction. So what we want to do is we want to take a negative out here through factoring, okay? So if I factor this negative 1 out here, it leaves me with a positive x minus 5. So at this point, we're going to rewrite the function as this right here, the x minus 5, as one of our functions, and everybody else is going to kind of be lumped in the other one. So I'm just going to put it up here so you guys can see it much better. It's the limit as x approaches 5 from the left of 1 over x minus 5. And then you're going to multiply that by the limit as x approaches 5. From the left. By the way, I'm going to bring you guys closer so you can see everything that I'm doing right now. There we go. Of everything that's not here. So 3 times 4 minus x over negative x times 5 plus x. All right. So this isolation is a negative infinity. This over here is just a straight plug-in. I know we're not normally used to plugging in 5 from the left in places like this, but you can just plug in now, because there's not a domain issue preventing you from plugging in. So it'd be 3 times 4 minus 5 on top, divided by negative 5 times 5 plus 5. Long story short, negative 1 times 3 is negative 3. The bottom is 5 plus 5 is 10 times negative 5. V5 full fum is negative 50 And there's a lot of negatives floating around, so I'm just going to say a negative divided by a negative is a positive. And a positive number, no matter how small, as long as it's a constant, being multiplied to or divided from negative infinity, is going to keep it at negative infinity. All right, let's try number 6. Oh, it's the exact same thing, except it's from the right. So none of these moves changes. Except here, from the right, is positive infinity, which changes our answer to positive infinity. That's it. What else we got? All right, piecewise limits. Okay, and I included absolute value in this because last year in pre-calculus I taught you guys how to convert piecewise defined functions from absolute value into piecewise. And here's what you do. You find the critical numbers that exist for the zeros inside the absolute value. So x equals 1 is going to be critical to the piecewise. It means that the piecewise is going to do something when you're less than 1 and something when you're greater than 1. And since it's on the bottom part of the fraction, I wouldn't put an equal to kind of fill in that hole, because you can't divide by 0. So if you pick a number that's less than 1, say 0, if you plug it in there, 0 minus 1 yields a negative value, which is kind of code for saying this part of the absolute value on the bottom is going to manifest the negative version of x minus 1, which is negative x plus 1. Which negative x plus 1 is the same as 1 minus x. Negative x plus 1. It's 1. Anything divided by itself yields 1. So it kind of looks like the function is a y value of 1 starting at x equals 1. It just looks like this. And then greater than 1, the inside of the bars manifests just the positive version of x minus 1. So the positive version of x minus 1 under sort of like the negative version of x minus 1 is going to make this negative 1. All right, the limit as x approaches 1 from the right is use that part of the piecewise, which there's no place to plug in for x. So it's literally that value right there. There's my final answer. So a similar thing's going to happen with number 7, but as you can see, nothing from the top is going to cancel with the bottom. We know that 7 is going to be the place in which it splinters off into two different parts. So I'm going to say x is less than 7 and x is greater than 7 are going to be our two domain parts. And you guys can't see that. So let's get you closer here. Pick something less than 7. Say 0. 7 minus 0 is a positive value. So this will manifest the positive version of 7 minus x. This, therefore, will manifest the negative version of it, which is negative 7 plus x, or x minus 7. From the right is this one. So, I'm going to say the limit as x approaches 7 from the right of this function is the same as 3 times 1 over x minus 7. You know, the whole split apart deal, which gives us 3 times, from the right, positive infinity. All right, so what happens when you just are given a piecewise? Well, all you got to do is just find the behavior from the left, from the right, and then make sure if the two y values match, then x equals 4 limit would actually exist. All right, sorry. Getting a little fatigued. I can do this. So this right here, less than would indicate a left. The function x squared minus 5x will exist everywhere, including 4, but left than 4 as well. So when you see less than, you're thinking x approaches 4 from the left. That's the portion of the piecewise we're going to use to solve part A. So it's kind of like saying, hey, what's the limit as x approaches 4 from the left of x squared minus 5x? There's no domain issue there. So it's just 4 squared minus 5 times 4, which is 16 minus 20. It's negative 4. Limit greater than is the x approaches 4 from the right, so that's the one we would use for B. So you'd say, what's the limit as x approaches 4 from the right of 8x minus 8? Again, there's no domain issue there. Plug in 4 here. It also equals negative 4. And that's really the test for whether or not you're even going to get an answer for part C. If these two don't match up to the same y value, it means you've got like a break in the graph, all right? Where it's like they don't converge to the same value. Does not exist. But for this particular example, they do converge to the same y value. So the limit exists since the limit as x approaches 4 from the left equals the limit as x approaches 4 from the right, which is negative 4. And that's what the limit at 4 is. I have 2 more examples for you. Number 9 is kind of tricky because I gave you one where you're spotting that x plus 1 and you're thinking, domain issue, domain issue, domain issue. But the domain issue does not match up with the limit that we seek. See, we're very curious about x approaches 4 from the left and the right. But negative 1 is nowhere near 4. So here's the deal. The less than informs our limit from the left. Is 4 a domain issue? No, 4 plus 1 is 5 on the denominator. So you can do just a straight plug in here. This is the limit as x approaches 4 from the left of 3x minus 1 over x plus 1, which is 3 times 4 minus 1 over 4 plus 1, which is 12 minus 1, 11 over 5. It's 11 over 5. Nothing special there. And then 4 from the right, you're going to use this function. There's no x to plug in 4, so you got to think, oh, it's just a constant function at y equals 7. Limits of constant functions should be the value of that constant function. Since the limit does not match the left and right, the limit here does not exist. Okay? That's just how it is. All right, and here's our last one. Hopefully you've had the endurance to last the 16 minutes and 34 seconds so far. Hang with me just for one more example. You got a piecewise that just, it doesn't have a less than or a greater than. It's just got 3x, and then a not equals, and then 9, and a does equal. So I'm going to sketch this really quick. It said the function equals 3x, but x can't be negative 1. Okay. Well, I know the function 3x looks like this. It starts at 0, goes down 3, left 1, but it can't equal x equals negative 1. So I'm just going to put like an empty space here, like a hole in the graph. Keep continuing with the slope. It's going to be a linear equation, except at negative 1, it equals 9. So here's negative 1. It's literally the point negative 1, comma 9. So it's up here. So you got to dig a little deep. Remember our graphing training on all this. From the left, it equals negative 3. From the right, it also equals negative 3. Now, so many people want to say that the limit as x approaches negative 1 is 9 just because the limit only exists if the left matches the right. And that is what the limit is. You know what this point represents? This point represents the function at negative 1. The function at negative 1 equals 9. The limit as x approaches negative 1 is trying to be negative 3. It's trying to be a function that holds it all together and remains continuous. It just, for some reason, at negative 1 couldn't handle it. All right. 19 minutes is enough. Hope you guys enjoyed it. Hopefully this stuff is helpful. Let me know if you have any questions. Bye.